Learn how the Wheatstone Bridge works, the principle of operation behind a Wheatstone Bridge. Right on the board is a schematic arrangement of 4 resistors that represent the Wheatstone Bridge. Okay, so we have R1, R2, R3, and R4. The arrangement of these in this format gives rise to what we call the Wheatstone Bridge. So we're going to learn how it works, or the principle of operation of a Wheatstone Bridge. The first thing we need to understand here is the analysis behind the diagram. This is the cell, and what happens at this point is that the cell supplies energy, current, to the circuit. So once the switch closes, current flows. The total current flowing through the circuit is this, flows, and then gets to this point, split into current 1, flowing into resistance 1, and then current 2 flowing into resistance 3. Alright? The same thing happens at this point. Current 1 comes to this point, flows into resistance 2, current 2 comes to this point, and then flows into resistance 4. Alright? So that's what happens. Then the next thing we need to understand, if current flows, what happens to G? G is a letter used to represent a device known as galvanometer. A galvanometer is a sensitive device that detects and measures. It does 2 things. It detects and measures. So it detects small amount of current flowing around the circuit. After detecting it, it measures it to give the quantity. So that's it, what makes a galvanometer so sensitive. Its ability to detect and measure the amount of current flowing around the circuit. Alright, so having said that, so if the key is closed, current flows. And once current flows, the galvanometer pointer begins to deflect clockwise, okay, showing that there is current flow in the entire circuit. Once the key is open, what happens? Current stops flowing and the galvanometer pointer returns back to 0. And that is okay. Now suppose we have an unknown resistance, maybe R1. We don't know what this is all about. We don't know the value of R1, okay? But we know the values of R2, R3, and R4. So for any unknown value of any of the resistances, we can find out by varying the entire system to find the unknown value. But it will get a point that under the situation that the values, there is a variation in the values of the resistance boxes, there will be no deflection. I repeat, there will be no deflection on the galvanometer pointer. I repeat, if any of these resistances is varied, a point will be reached where there will be no deflection on the galvanometer pointer. That point, the branch B and D is at the same potential. So there is no current flow, and that is why the galvanometer does not show any sort of deflection. So what do? We need to use some mathematical representation to find the unknown resistance. Alright? And then before we delve into all that, I think it's time for me to urge you to subscribe. Subscribe to this channel, okay? Right? Give us some thumbs up. Share with your networks, students, friends, and everyone that loves something like this. Don't forget to put on the button for constant notification each time contents like these are uploaded. Alright, having said that, let's move into deriving the general formula for finding the unknown resistance. It could be resistance 1, resistance 2, resistance 3, or even resistance 4. So anyone goes. Alright, so what do? We find the potential difference across this branch, which is A, B, and then potential difference across B, C, After which, potential difference across AD, and then potential difference across CV. So that's what we're going to do. Quickly, without wasting time, PD, all right, PD across AB, that's this, will be equated with PD across what? BC, right? It's going to be equated with PD across BC. Then we're going to do this at the same time. PD across AD will be equated with PD across CD. So we have PD across AD being equated with PD, that potential difference across CD. So that's what we are going to generate. First equation from here, the second equation we are going to generate it from this point. So let's see how it goes. All right. So quickly we look at that. PD across potential difference across AD is this. This is the branch that represents it. So we have I1, okay, R1 is equal to PD across BC, and now we have I2 and then R2. That's, we call this equation number 1. Equation number 1 is this. That is clear. Then we look for potential difference across AD. This is the branch AD. We look for potential difference across this branch, and that will give I2, okay? That will give I2, and then R3, good. And we have is equal to, okay? Is equal to potential difference across CD, and that will give us I2, all right? And then R4. This is equal to, this becomes our equation number 2, respectively. So having done this, the next thing we need to do is to divide through, okay, with equation 1. By the time we divide through with equation 1, we have I1 R1 all over I2, all right? R2 is equal to I2, right? R3 over I2 R4, okay? We call this equation number 3, all right? That gives us a clear representation of what we're looking for, right? So the next thing we need to do, we cancel out. We cancel out. We are necessary. We cancel out. Because this is going to be, this is I1, not I2. This is going to be I1, because that's what we're dividing all through, right? So we cancel out because I1, look at it, I1 flows into this. So this should be I1. This is I1, okay? Good. So what do? We cancel out. I1, we take care of I1 at this point. I2, we take care of R2 at this point. And finally, we are left with R1 over R2 is equal to R3 all over R4. This becomes our equation number 4. Good. So that equation is the general equation for finding any of the unknown resistance given in a Wheatstone Bridge circuit. So with this, we are good to go. Suppose R1 is unknown. Suppose we don't know the value of R1 resistance. What we do? From this equation, we make a resistance 1, the subject, and that becomes R1 is equal to R3, okay, times R2 all over R4. Very simple. So with this, we can find R1. We move on again. Suppose we now know the value of this. We want to find this. We make R2 the subject. It becomes R2 is equal to, by the time we do that, it becomes R2 is equal to R1 times R4 all over R3, and so forth and so on. Okay? So that's what that's how to use the formula. If we are given that, we make one that is unknown, the subject, and then use the values of the known ones to find the unknown. Having watched up to this moment, I want to thank you so much for your patience. Don't forget, subscribe. Especially my returning subscribers, thank you so much. And my new subscribers, please, you're welcome. Alright? Subscribe, give us some thumbs up, always share with your friends, network students, and whoever that is interested in things like this. Put on the bell button for constant notification. Do not forget, so that each time content like this are uploaded, you'll be among the first set of individuals to be notified. See you in my next class, where I will be solving 1 or 2 exercises on how to use this particular general formula concerning Wheatstone. I'll be linking it there or somewhere there. Thank you. And